So today we're going to tell you about limiting and excess reactants. Basically, limiting and excess reactants are a way of looking at a stoichiometry problem when there is more than one amount of a reactant given, and you have to figure out which one is going to run out first and give you the correct answer to the problem. So here's the idea basic idea with limiting and excess reactants. When two or more substances in an equation are reacting to form new substances, they have to sort of work together. In other words, neither one can carry out the reaction by itself. It's kind of basic idea that without both chemicals, or if there are 3 or 4 chemicals, you can't have a reaction occur without every one of them being present. And when one of the substances runs out, the other one or the other ones cannot go any further, even if they haven't run out yet. So if I'm making sandwiches, peanut butter and jelly sandwiches, and I run out of bread, I might have jars and jars of peanut butter and jelly, but I can't make any more sandwiches without more bread. So as soon as one thing runs out, I'm kind of toast. Well, that was a completely inadvertent pun, but a pretty good one. So in this picture, you see there's a 3-legged race going on with a bunch of kids in a park. And you see in the middle here, there's a kid that's about to fall down or has started to fall down. The idea with limiting and excess reactants is that when this kid falls down or tires out and falls over, the other kid, even if he's got lots of energy, can't go on any further. Okay? You're going to have to drag your partner along by the ankle, and that usually doesn't work for very long. And so you can't go further. Even if you have lots of energy and your partner has fallen down, you're sort of done. In chemistry, in a reaction, there is no picking up your friend and carrying them. There is no throwing them over your shoulder. There is no dragging them along till their ankle breaks. That just doesn't work. So in chemistry, the chemical that runs out first will limit the reaction from going any further. The same idea here. This guy on the left seems to want to pull his partner along. Well, that's not going to work. He seems to have energy left. This other kid laying on the ground here has fallen down and is out. And when that one runs out, both of them are limited. The idea being that you're only as strong as the first one that's going to tire out. So if I'm running a marathon tied to you, well, I hope you're in good shape because we're not going very far based on how fit I am. Well, in the same idea with the chemical reaction. So when one chemical runs out, the other one has to stop as well. And that one that runs out first will limit how far the reaction can go. Well, in a picture, it's easy to tell who's run out first and who's limiting the reaction. But in a chemical reaction, we can't always tell. In this example reaction, we see a combustion reaction, and this is true of any sort of reaction when there's more than one reactant on the left side of the equation. The idea is that one of the reactants, either the C3H6 here, will run out first, or the oxygen will run out first. And when one of them is used up, the other one has to stop the reaction as well. When we run out of fuel, combustion stops. When we run out of oxygen, combustion stops. And this is true of any reaction as well. Even if there's plenty of the other one left over, the reaction has to stop. And you can see this in everyday life with things like a bonfire. When the wood burns up and is gone, there's plenty of oxygen left around, obviously, but the burning stops. Rarely do both chemicals run out at the same time. In chemistry, there are times when it's very important that they do, but most of the time one chemical runs out and the other one is left in abundance. There's lots and lots of it still there. When we're baking in a kitchen environment, perhaps, we want to plan so that all the chemicals are sort of running out at the same time. Otherwise, you have a lot of leftover something in your recipe. So if I bake cookies with way too much flour, there might be chunks of just raw flour in my cookies or bread, and that's no good either. So in recipes, basically, we're trying to plan it so that everything runs out perfectly together and tastes good. So the idea is that a limiting reactant is the one that runs out and limits how far the reaction can go and determines how much product we can make. It's really important to identify the limiting reactant because it's going to tell us how much we can actually produce. Which ingredient's going to run out first, if you will. And the excess reactant, or even reactants, if there's more than 2 on the reactant side of the equation, you might have 2 or 3 or more things that are in excess. Once the first thing runs out, the other things are left in excess. And in peanut butter and jelly sandwich example I gave earlier, when the bread runs out, the other 2 things, the peanut butter and the jelly, are still left. Lots and lots of them left over. Excess reactants are in excess or left over when the reaction stops. So let's say in this example of combustion, we want to figure out how much carbon monoxide can be made. So here's my carbon monoxide. And I've got some amount of both C3H6 and oxygen. And I need to figure out which is going to be the limiting reactant, which is going to be the excess reactant. Well, what we would do is we would do stoichiometry twice. You do it once, starting with C3H6, figure out how much carbon monoxide you can make. And then you'd get an answer there, and then you'd repeat your stoichiometry, but you'd start with your oxygen, and you'd solve for your carbon monoxide the second time. And you'd get 2 answers, and each of one of them would be an amount of carbon monoxide, a mass or a volume or something. And what you do then is look at those 2 answers and realize that the smaller one, the lesser answer, is the correct one. If I have enough, bread to make 10 sandwiches, but enough peanut butter and jelly to make 30, I'm only going to be able to make 10, the smallest answer of those two. In the example of our reaction here, if the C3H6 can produce less than the oxygen can, then the C3H6 is going to run out first, and the oxygen will be in excess. So the smaller answer is correct when you have two or more answers. The smallest answer is correct. And the larger answer or answers can't happen, because that one is in excess and the other one has already run out. So again, think about it as our idea of a three-legged race. The shorter distance, the shortest distance that any one of those two that are tied together by the ankle can run is the distance that both of them will be able to go. Whereas if the other person's in good shape or stronger or could run further, even if they could run further, they can go no further because the first one has run out and fallen down and they're stopped right there. And they're probably going to lose the race. In chemistry, it works out the same way. One of the reactants could go further, but the other one has run out, so the reaction is over. So what we want to do is go through an example or two of the kind of problems where this would look, and you're going to find that the stoichiometry here looks basically the same as every other stoichiometry problem that you've done. In fact, you might find these are relatively simple, even compared to some of the ones that you've already done. As with all equations, we want to have a balanced equation first. And again, I'm not going to take a lot of time with balancing on this because I know you can handle balancing equations. This one comes out as 47866 for our coefficients up here. So we'll assume that you can handle the balancing on this. And you can see in the problem that it's giving me the question here to say if 18.4 liters of C2H3F3, that's this stuff, are reacted with 64.1 grams of oxygen, that's this here, okay, how many grams of fluorine, way over on the other side, will be produced? So this is kind of a three-part question. We've got three chemicals that are being either given information for or you're being asked to find. When you have stoichiometry problems going, as always, you can only use two substances in a given stoichiometry problem. You can only study two at a time. So how can we study three at once? Well, we don't. We start with, as I mentioned earlier, you start with either one of the two numbers and solve for the same ending answer twice. In this case, I'm going to start with my 18.4 liters of C2H3F3. And I'm going to do stoichiometry right through to the end. And what am I solving for? Well, the question's asking here, how many grams of fluorine? So this is what we're going to try to find at the end of the problem for both the stoichiometry problems we're about to do. Now, I won't take a lot of time with the stoichiometry because you guys have done a lot of these by now and you should have a pretty good grip on how to do basic stoichiometry problems. We're going to use those same constants we've been using all along, knowing that 22.4 liters of any gas at STP, standard temperature and pressure, is 1 mole, and we're still assuming we're working at standard temp and pressure. And then we get to the mole ratio. We want to solve for fluorine. So according to my equation, 6 moles of fluorine will react from or be formed from every 4 moles of this C2H3F3. So as we go on here, we're going to solve for grams of fluorine, right? And so the last step, like usual, is to get to something other than moles. We usually don't want to stay on moles, and we'll go to grams or liters. Here we're going to grams. So I go to my periodic table, I look up fluorine, and because it's a diatomic element, I need 2 of them. And so it's around 38. You could use 38 grams here too. And I set up my stoichiometry. So I've started with my C2H3F3, and I'm solving for my fluorine. And according to all this, I can go through and punch it in and cancel out my units, and you should certainly make sure that those units do cancel out. At the end, this answer comes out to be 46.8 grams of fluorine. Now, if that was a normal stoichiometry problem, that would be our answer and we'd be done. But in this question, we were given another amount. We were given 64 grams of oxygen as well, and we haven't used that yet. So when you have two numbers to start with, one for C2H3F3 here and the other for oxygen, we have to do stoichiometry again, and we're going to do it starting with the other amount this time. 64 grams of oxygen. How much fluorine could I make from that? Okay. These are the two partners in our three-legged race, if you want to think about it. And this plus in the equation, sort of like that little rope around the ankles or that handkerchief that holds them together. These two have to go together. And so as one runs out, the other has to stop. We need to figure out which one can go a shorter distance and which one can go a greater distance. And in doing two stoichiometry problems, we'll get the answer. So again, pretty simple stoichiometry here. You've done many of these. I won't spend a lot of time with talking about the numbers, but about 32 grams of oxygen per mole. Here we're working with grams, so we want those units to cancel out. In our ratio, According to our chemical equation, 6 moles of fluorine, that's the same as our previous one, can form from every 7 moles of oxygen. So make sure to watch those coefficients and bring them down. And then the last step is going to be the same as it was up above, because we're still trying to get to grams of fluorine. We're just having started in a different place. So my last step is going to say, again, around 38 grams, and I'll use the same number just so it's consistent. 38 grams or so of fluorine in every 1 mole of fluorine. And when I punch that in my calculator, I get another answer. And this time it's 65.2 grams of fluorine. Now here's the thing, which of them is correct? Of course, it's the lesser one, because it says to me then that this first reactant, my C2H3F3, can only make 46.8 grams of fluorine. The oxygen could make more, could go further. Again, one more time with the analogy of the three-legged race, it's like saying I could run 46.8 yards and you could run 65.2 yards. Well, that's great for you, but we're tied together, and so we're only going as far as the shortest one allows us to go. In here, it's mass. The C2H3F3 could make 46.8 grams of fluorine. The oxygen could make more. It could make 65 according to this reaction. But it can't, because the fluorine is limited by the one that runs out first. Okay? The fluorine amount being made here at the end is limited by the one that runs out first, and that's this guy. So if we're to identify them as limiting and excess reactants, and this problem and this practice page that we've given you is going to ask you to do that, this then is my limiting reactant. It's the one that ran out first. And the oxygen would be the excess one. At the end, some of this 64.1 grams of oxygen is going to be left over. Okay? It won't all have been used up. Again, it's like the end of that race. If your partner quit on you or fell over, you've got energy left, and now you're probably pretty mad too. But you've got energy left over. Your partner is completely spent, and you've got energy left over. So you're the excess reactant because you've got energy left to spare. That's the idea on a stoichiometry problem with limiting and excess reactants. And we'll go through another example and post it on the next video.